Hello, hello everyone. Good afternoon, and welcome to the 12th International Topical Meeting on Industrial Radiation and Radio Measurement Applications. I am Iman, and I'm gladly hosting this session with my colleague Jamila. We will start our session according to the list uploaded on the website. I encourage each speaker to write her or his email on the chat, so audience can send their valuable questions and feedback. Now we will eagerly start with our speaker, Mr. Saud.
I work at the University of Surrey in the United Kingdom, and I'm going to speak about lanthanum bromide detectors equipped with silicon photomultipliers. So before doing that, I would like to thank the organizers for giving me this opportunity to speak to you today as part of this very well-known conference series. So let me start. Yeah, so lanthanum bromide detectors are relatively new developments in the last maybe 20 years. They are scintillation detectors which have relatively good energy resolution, at least relatively good energy resolution compared to other older scintillation detectors like sodium iodide or barium fluoride. And that means that about 3% of full width half maximum at 662 keV of the cesium source. And you can see a typical spectrum here on the right. Yeah, so that means that in many applications, it overtook the old scintillation detectors and because of its properties. Another important property that they are very fast. So I will speak about that quite a lot. They have a very good time resolution, as I will show. And that is very important in many applications. So you can imagine these detectors are used in environmental science or medical science. And for example, in positron emission tomography, where two gamma rays have to be detected at the same time, the time resolution is very, very important factor, as good timing resolution allows a much cleaner, noise-free image to be made with SPECT, for example. In our case, at the University of Surrey, we use these detectors for nuclear physics science and to measure lifetime of excited state of the nuclei. So in order of from 10 to picoseconds to nanoseconds. Yeah, so here I'm showing the basic principles of ultra-fast timing. We have a source which emit maybe decays by beta decay or emit gamma rays after that, like shown here on the left. And we have two detectors. Let's say these are two lanthanum bromide detectors. And if you want to measure the lifetime of this state, excited state here, which is fed by gamma 1 and depopulated by gamma 2, we can measure one gamma ray in one detector, other gamma ray in other detector, and we put start, one is start, other is stop, and we put in a time amplitude converter and measure the time difference between these two. And that should give us the lifetime of this intermediate state. If the lifetime is relatively long compared to the time resolution of the detector, then we have a slope, and from the slope we get the half-life of that. But we can measure much shorter lifetime than the time resolution of the detector, in our case in order of 10 of picoseconds. If we look between just shift between centroids, the two lines here, red and blue, is one of them when we detect gamma 1 in detector 1 and gamma 2 in detector 2, and other when we invert them. So invert the start and stop signals, meaning that gamma 2 is detected in detector 1 and gamma 1 in detector 2. And this shift between them will give us the lifetime. Yeah, so if we have a lot of statistics, we can measure down to tens of picoseconds. And in our case, in nuclear physics, this is important because this information can give us information about, for example, the size of the nucleus, the shape of the nucleus, whether they are spherical nuclei or deformed nuclei, and other information about the wave functions. Yeah, so in Surrey, in the UK, I should say Surrey and Brighton, we developed an array, we call it fast timing array for this packet fair. This is in Germany, a large collaboration based on these lanthanum bromide detectors. This shows the size of the crystals, 2-inch long crystals, and 1.5-inch diameter crystals. These are relatively large to be able to have reasonable efficiency for high energies, but not too large, relatively small in other sense, because smaller detectors have better timing resolution. Normally, these are coupled to photomultiplier tubes, and this is shown on the photograph as well. This small here at the end is the crystal and the long photomultiplier tube. We have 36 of these put in an array. Yeah, so these crystals have a slight disadvantage for some application that there is some background radiation associated to them. Lanthanum, so lanthanum obviously, it is in lanthanum bromide detectors. 99.9% of lanthanum is 139 lanthanum, which is stable, but about 0.1% is 138 lanthanum. Yeah, and this has a half-life of 10 to the 11 years, so it's much longer than the age of the universe, and it's there in every lanthanum detectors, and it slowly decays, and it decays by electron capture, leading to this gamma ray here, 1436, or a smaller fraction decays into this other one in cesium, which has another transition. Here on the right, I'm showing the internal radioactivity of one of these detectors. So you can see this is a logarithmic scale. We can see the barium X-rays. Yeah, because lanthanum decays into barium. We see this 1436 keV transition plus X-rays, because X-rays are emitted after electron capture. And we see this other gamma ray as well. In addition, we see the beta background here. At higher energies, we can see alpha lines. These are from actinide nuclei, which have very similar chemistry to lanthanum. Yeah, so in the case of our detectors, which 2-inch long and 1.5-inch diameter, this is a rate about 73 Hertz on average. Yeah, so it's considerable rate. So this might be a disadvantage in some cases, but in our case, we want to measure lifetime. It doesn't matter really, because we measure in coincidence. So we require 2 detectors to fire at the same time within nanoseconds time window, and that is not a problem for us. Yeah, so as I said, we have 36 detectors. I'm showing here how it is organized. It's in 3 rings. So here just half of the array is shown. There is one ring at 90 degrees, one at forward degrees, and one in backward degrees. Our source area is relatively large. That's why we need this large number of detectors. This is what it looks like. So I have to move this picture. Here it's a photograph. I'm showing you can see one ring here. It's 2 detectors missing. Our source area will be here in the middle, at least 8 centimeters by 8 centimeters. And here it's shown the array with, in other photograph, these are the lanthanum bromide detectors here. And there are additional germanium detector here in the setup. This is positioned now at GSI in Darmstadt, at the GSI facility for nuclear physics. And yeah. So this array is exists already for some time, a few years now, and it was used in several different places. So here, picture B shows in our laboratory in Surrey, but it was used also in the United States Argonne National Laboratory. Picture here. These are other pictures below here. They were used in France, in Orsay, and also at Ganil, also in France, near Caen. And this picture here, it's in Riken in Japan. So these detectors are easy to bring to different facilities, and that's what we did in the recent years. So originally, these are equipped with photomultiplier tubes, and these are the standard way of operating scintillation detector. But in the recent years, silicon PM, silicon photomultipliers, became available, and we were looking into modifying the array to make it possible to use these silicon PMs. And why we do that? So there are a couple of advantages of using silicon photomultipliers. So on this figure, I'm showing again the array, and you can see that these detectors cannot go closer to the center because they touch each other, but not the detector touch each other, but the photomultiplier tubes. The photomultiplier tubes have much wider diameter. The active area is 1.5 inch, the same like the crystal, but the total diameter is much larger, therefore they touch each other. So if you manage to make it much smaller, like in the case of the silicon PMs, these detectors could go closer, and therefore the efficiency will be larger. Another problem is that very often we make measurements in laboratories where there are magnetic fields. There are magnets used to select nuclei and fast-moving ions. And magnetic fields interfere with photomultiplier tubes. So this graph shows this. This was measured in France. This is a current on a magnet. So this is proportional with the magnetic field. And you can see that the energy resolution, these are gamma rays coming from Europium-152 source, energy resolution gets worse and worse with magnetic field. It doesn't matter really, because in Darmstadt, the GSI facility for nuclear physics. And yeah. So this array exists already for some time, a few years now, and it was used in several different places. So here, picture B shows in our laboratory in Surrey, but it was used also in the United States Argonne National Laboratory. Picture here. These are other pictures below here. They were used in France, in Orsay, and also at Ganil, also in France, near Caen. And this picture here, it's in Riken in Japan. So these detectors are easy to bring to different facilities, and that's what we did in the recent years. So originally, these are equipped with photomultiplier tubes, and these are the standard way of operating scintillation detector. But in the recent years, silicon PM, silicon photomultipliers, became available, and we were looking into modifying the array to make it possible to use these silicon PMs. And why we do that? So there are a couple of advantages of using silicon photomultipliers. So on this figure, I'm showing again the array, and you can see that these detectors cannot go closer to the center because they touch each other, but not the detector touch each other, but the photomultiplier tubes. The photomultiplier tubes have much wider diameter. The active area is 1.5 inch, the same like the crystal, but the total diameter is much larger, therefore they touch each other. So if you manage to make it much smaller, like in the case of the silicon PMs, these detectors could go closer, and therefore the efficiency will be larger. Another problem is that very often we make measurements in laboratories where there are magnetic fields. There are magnets used to select nuclei and fast-moving ions. So, and magnetic fields interfere with photomultiplier tubes. So this graph shows this. This was measured in France. This is a current on a magnet. So this is proportional with the magnetic field. And you can see that the energy resolution, these are gamma rays coming from Europium-152 source, energy resolution gets worse and worse with magnetic field. This depends on how far the detectors are from the magnet. The inner ring is closer, so it gets faster, get a better resolution faster, while the outer ring is less affected because the detectors are farther away. So all these two problems, the size, making smaller, and also being not bothered by the magnetic field, disappear if we use silicon photomultipliers. And this is what we developed. So this was developed in collaboration with the Research Institute, Nuclear Physics Research Institute in Bucharest, in Romania. And this is what it looks like. So again, here is the crystal, you can see, and this is the electronic part, is the silicon PM. So you can see that while previously the photomultiplier tube was much larger than the crystal itself, here in the case the crystal dominates in the very small area here. So the diameter is just slightly larger of the detector than the crystal itself. So this shows the photograph. You see the diameter is slightly larger and show the different connectors. And this is the active area of the silicon PM. So I will say more words about the silicon PM itself because that's the most interesting part. And yeah, so I said that it's very compact. We have silicon PM cells. You can see these cells here. We try to cover the whole area of the detector, which is 1.5 inch diameter. These are 6 by 6 millimeter cells. We have 26 of them. And in the corners here, where there is no enough space, we put 3 by 3 millimeters ones. Yeah, and with this relatively well, we can cover the full area. We make it compact by keeping small distance, 0.1 millimeter between the cells. And in this way, we cover 86% of the area. So these cells are bought from onsemi, which is SenseL, was the former company name. So these are very well known. So you might know the silicon PMs have microcells. These are photodiodes, which either trigger or not. So a 6 by 6 millimeter have 22 photodiodes in it, or microcells. So that means that in total, each of these can measure a photon or not measure a photon. Yeah, so it's a large number. A field factor is 75% for the 6 by 6 and smaller by the 3 by 3. And the photon detection efficiency is around 50%, as it's given here. Yeah, and it's important that also have a dark current, and this is given here with the dark current 150 kilohertz per square millimeter for the two types. Yeah, so the electric board was developed by our Romanian colleagues and is shown here on the right-hand side. It has 3 boards. One of them which contain the silicon PMs, and you can see the photograph again, as we discussed in details. And then the signal goes to a preamplifier board, an intermediate board, the preamplifier board here, which has 2 outputs, has a slow output, which is used for energy measurement, and has a fast output, which we use for fast timing to measure the time. In addition, we have a third board, and this is used for gain compensation. Yeah, the third board is here. The gain compensation is based on the PT100 sensor. This measures the temperature. It goes, the information is digitized and go to the microchip, and this microchip controls the voltage on the silicon PM. So by choosing the appropriate voltage for different temperatures means that we have we keep the amplification constant, and I will show you this one later. So this is very important because the silicon PMs are very sensitive on temperature changes. Yeah, so if we want to see how they behave compared to photomultiplier tubes, so these are the same detectors, same kind of detectors. We have 36 of them with photomultiplier tube and with silicon PM. And you can see these different sources, 137 cesium, and you can see that the resolution is even better a little bit with silicon PM compared for photomultiplier tubes. And the same with 152 europium source. The obvious way to see it is this high energy peak, while here we can see a shoulder at 1408 keV with silicon PM. This is much clearer that there are two different transitions there. Linearity is an important factor, and while silicon PM are relatively linear up to this our 1.5 MeV one, you can see this curvature for PMTs showing that it's less linear than our silicon PM. So if we compare this energy resolution, this is shown in fraction of in percentage as function of energy, you can see that for all energy, the silicon PMs behave better. The difference is not so huge, really, but the silicon PMs, anyhow, they have better resolution with detectors with silicon PMs for all energies, slightly better. What about timing? And to measure time, of course, we have to measure time difference between two different detectors. So the best time resolution detectors are small and have a conical shape. And you can see that the best time resolution between conical detectors themselves. And we compare this one with one conical detector in one detector, another detector, a cylindrical PM detector with photomultiplier tube. Yeah, so this will get information on our detector, and this is shown again here as a function of zero cross voltage. Yeah, so you can see around 230. So if we change this detector for silicon PMs, this is the curve. So if you look at the numbers, these are very similar. Yeah, so this is the final version, really, comparing them. So when we have two conical detectors, they are much better because of their shape and size. So the black one, that's 180 picoseconds, full width half maximum. If we change to our detectors, our cylindrical detectors, the red and the green lines, they have practically the same time resolution. Yeah, so it's within error bars, really. So the PMTs have a little bit higher than the silicon PM at 230, but they are the same. Yeah, so I mentioned before the temperature compensation, and I show here what it means really. So on the upper part, we see a cobalt spectrum, or better said, 10 cobalt spectra from 10 energy spectra, measured at different times and at different temperatures. So temperature difference within 3 degrees, only 3 degrees Celsius difference here. And you can see the big differences on amplification and the position of the two cobalt sources. Yes, when we add them up in a single spectrum, the energy resolution is 41 keV, which is not so good. So if compensation is on, measuring the temperature of each silicon PM and compensating through the voltage on them, you see even if the temperature range is higher than there, 4.7 degrees, the energy resolution is kept below 5 keV. You can see that this time 10 spectra are on the top of each other. So it works very, very well. Yeah, so this is what we developed. I would like to show in the remaining of the time what we are using this for. Yeah, so we are using it for nuclear structure studies to measure the properties of nuclei, and how we sell this to the general public. Why this is interesting, because this gives us information how the elements, and specifically how the heavy elements, were created in nature. We know that these were created probably neutron star merger or supernova explosions. But exactly how, we don't know. And to do that, we have to understand the properties of nuclei, which are neutron-rich. Yeah, so this shows the nuclei chart with the neutron number on the x-axis, proton number on the other axis. The black data points are the stable nuclei. And in order to understand the abundances of different elements produced in this process, we have to study nuclei up to this red line, which is the R process line, rapid neutron capture line. So all these nuclei from the stability down to this part have to be understood, because they have influence the amount of elements we create, or different elements. And I will show you one example now, which is 190 tungsten. So 190 tungsten is radioactive, a neutron-rich nucleus. This is a level scheme. And here we measure the lifetime of the 2+ excited state. This is the first excited state in this nucleus. So for that, we have to measure the time difference between the 207 keV and 358 keV. So we can see that these are in coincidence. If we gate on one of them, we can see the other one, and opposite. If we gate the second one, we can see the first one. In order to do lifetime measurement or short lifetimes, we have to understand very well our system, not only the detectors, but also the data acquisition. And this is done with high statistics measurements with a europium source, 152 europium source. And here you can see the time spectra between two transitions, 779 and 344. And in the other case, the black one, we change the start and stops. So the lifetime between the state of the has a lifetime is close to 0, but you can see these two lines do not coincide. And this is because the time is the measured time is affected by the energies. Practically, the electronics have different time response for different energies. So so therefore we have to understand this prompt response difference. That's what it's called. And this can be done with a europium source, because it has several gamma ray transitions, and you can see there is a fit on them. So if we do this for our case, 207 and 358, the 2 gamma rays, you can see the statistic is much lower, because it's not easy to produce this nuclei, and you can see there is a shift. And from this shift, we can determine that the half-life of this is less than 200 picoseconds, around 190 picoseconds. So it's comparable to the timing resolution. So you cannot, of the detector, therefore we cannot see the exponential decay, but we have to look at this centroid shift method. Yeah, and I think it's time to conclude with this one. So in conclusion, I showed you that lanthanum bromide detectors are very popular nowadays in different fields. And we have developed a silicon PM readout for these detectors. And while the usual one, the more traditional ones are PMTs, and silicon PMs have excellent energy and timing resolution, similar to that of photomultipliers, to sometimes even better. And in many cases, silicon PMs are easier to use. So if you don't, the voltage is much smaller, lower than for PMTs. They are much smaller physically, these detectors, and they don't mind to be in magnetic field. Also, this readout has temperature compensation, as was showed, which is very important in this case. So this work was published very recently. Actually, it has a 2025 data on it in nuclear instruments and methods. So you can please have a look at them. So thank you very much for your attention, and I'm looking forward to your questions.
Good morning, dear colleagues. My name is Hector René Vega Carrillo, and we are going to present the work response of a passive TLD 600, TLD 700 regular parallelepiped Newton spectrometer. This work was carried out by Antonio Baltasar Raigosa and Professor Marcial Vázquez Arteaga. The motivation of this work is because during lighting in storms and in cosmic ray interactions, neutrons are produced. These antitelluric neutrons are the natural origin of neutrons. Also, in some anthropogenic activities, neutrons are produced. So therefore, regardless the neutron origin, it is necessary to measure the neutron spectrum and with the spectrum to calculate the dose. Due to the lack of electric charge and the ways of neutrons interact with matter, the measurement of neutron spectrum is not a trivial task. So there several efforts have been made to design neutron spectrometers using a set of moderators with moderator material and shape is changed, or with one moderator with several detectors. The outline of our presentation is an introduction, materials and methods, results and conclusions. Bonney sphere spectrometer was designed in 1960 and still is the most widely used spectrometer. The Bonney sphere spectrometer is a set of moderating spheres with different diameters having a thermal neutron detector in the sphere center. Here we show you different images in which Bonney sphere spectrometer are used to measure the neutron spectrum. Here is in a hospital. Here is trying to measure the neutron spectrum due to the americium source that has this apparatus that is used to measure the amount of hydrogen or the humidity in soils, for instance. Here is one experiment where the neutron spectrum of one americium source inserted in this neutron howitzer is measured. The Bonney sphere can have a small set of spheres or a large set of spheres, or have also different shells that are used together with the spheres in order to measure the high energy neutrons. Regardless the number of spheres or the moderator or the different items that are added to the spectrometer, is very important to know to calculate or to determine the response function or that altogether are named the matrix response. So the use of Bonney spheres for measuring the neutron spectrum from thermal to 20 MeV Newton is a well-defined technique. Even the inclusion of moderating spheres with high atomic number materials in shells extend the Bonney sphere spectrometer to few giga-electron volt neutrons. Here are two different designs that has been published, and here are the way that the addition of these shells, the inner shells, increase the response of this spectrometer to larger energy neutrons. Bonney sphere spectrometer needs a moderator and needs a thermal neutron detector. So this detector can be active detectors or can be passive detectors. Active detectors, the main detector used 3 isotopes: lithium-6, in this chemical compound in a scintillator, or in gaseous these isotopes in gas form, which are in proportional detectors. Or you can use passive detectors, in which the technique of pairs of TLD 600 and 700 is used due to the different concentration of lithium-6 in this type of detectors. Or you can use activation foils like gold, dysprosium, and indium. Here I included the samarium and gadolinium because there are no works of using or analyzing or calculate the matter response in Bonner sphere if you use samarium or if you use gadolinium. So in high intensity pulsed and mixed radiation fields, the use of Bonner spheres with active detectors is unreliable because the detector shows large dead times and pulse pileup. In order to avoid the large dead times and pileup pulses, in the active detector you have two approaches. One is you want to keep your active detector, you must to operate your detector in current mode. The other approach is to move your active detector and use instead a passive detector. So the reason, the three main isotopes that are used to measure the thermal Newton detector, helium-3, boron-10, and lithium-6, is the cross-section. Here are the cross-section of these three isotopes, and you can notice that for thermal newtons, let's say less than 1 electron volt are the thermal Newton region, the cross-section are large. The other approach is to use, for instance, gold and dysprosium, and also you can notice that for low energy newtons, let's say thermal neutrons, the cross-section is large. Here I'm including the cadmium because normally when you use one of these foils, you normally want to remove the thermal neutrons for the other energy neutrons and use like a filter the cadmium. Also, you can use indium. Here I'm presenting you the cross-section of the two natural existing isotopes in indium. And you also can notice that for low energy neutrons, the cross-section is large. Here are the gadolinium 155 and 157, which are the most abundant isotopes in natural gadolinium. And also, we can notice that the cross-section for low energy neutron is very large. And here I'm presenting you the samarium 149 and samarium 152, which are the two natural existing isotopes in samarium. And you also can notice that the cross-section for low energy neutrons are very large in comparison with the cross-section for high energy neutrons. Now we're going to discuss the different approaches to keep the idea of Bonner spheres by changing the moderator or changing the detector. Here, in a work published by Rahim Kabas in 2012, he proposed to change the moderator. Instead of using high-density polyethylene, use spheric shells that are filled with water. And he calculate the Bonner for each sphere, he calculate the function response. Also, these two colleagues, Blick and Pavlik, in 2018, they proposed to change the detector. Instead of using the classical gold or gadolinium, he proposed using indium, an indium foil. And he made the proposal of the design using this array in which you can change your detector for an active detector being a helium-3 proportional gas detector, or use a foil, a gold foil, and he presents the response. Another approach is to use nested moderator like the Matryoshka dolls. And here, the first work that was published in 2012, in another work published in 2021, this is the Newton nested spectrometer, which is a set of cylinders that can have an passive detector in a gold foil, and this is the matrix response, or you can change the detector in the center, can change for an helium-3, a proportional gas detector, and this is the response function. You can notice that regardless if you use gold or you use helium, you can notice that for the different moderators, the response looks similar. But what is very different when you use the Ver detector. This is practically the cross-section of gold, and this is practically the cross-section of helium-3. But for when these detectors are inside a moderator, the rest of the response function are very similar. Even you can notice that the value is very different. For instance, here you can notice that this 0.4 for this peak, and here for this peak you can notice that this 1. So one detector is more efficient than the other detector. But the important here that they come up with the idea of make a set of nested moderators, because to carry out or to move the large number of spheres is heavy, and it has some difficulties. But having a set of cylinders that can be put one nested in other is very compact. Well, the other approach is to use water as moderator and use a helium-3 detector and use several shells that are filled with water. And this shell filled with water, the response to neutrons are these functions that you can notice here. And if you observe the responses that I showed you before, looks very similar. Large efficiency for when the thicknesses of the moderator is small, and as we increase the thickness of the moderator, the response function is moving, the peak of the response is moving to high energy neutrons. Here is the another approach. This is a passive nested Bonner cube spectrometers with the same idea of the nested cylinders, in which the paper published the response function when you use a gold foil as a thermal Newton detector. Even here include the response when you include the gold foil bare and the gold foil covered with cadmium. And this is a set of response functions for each cube, and together are the matrix response. So now we change to when the people use a single moderator. A single moderator having inside many detectors. Here is this work that is published by Lisa and collaborators. When it's a single moderator and having in this position along all the axes have the different detectors, and these are the response function for each position of each detector. Recently, Professor Tunisak in 2024 published a paper which is now in press, in which he makes a very nice review of all the efforts made when people try to propose single moderator Newton spectrometers. This is another approach by Misokosti in 2016, in which they use different shells of polyethylene, and in between these shells you have this type of material, which is a transparent rubber sheet type, which is europium, lithium, calcium, and aluminum, and fluor 6. Here the isotope which detect the neutrons is the lithium 6, and they have fibers here, fiber like a light pipe, and these fibers have the signal of these transparent rubber sheets that are processed in this like a photomultiplier tube, and is treated these signals in a computer, and you can see that the detector, when you have the the most outer layer, the most external layer, the response, when you have less moderator, the response is very large for low energy neutrons. As you go inside the layer, as you increase the amount of moderator, the response is moving to larger energy neutrons. There is another approach by the group of Gomez-Ross and collaborators in 2012, which is a single sphere having in this position along this sphere 31 dysprosium foils. The polyethylene sphere is 25 centimeters diameter, and the response functions for each position for this detector allocated at this position changes. As I told you before, when the thickness of moderator is small, have a larger response to low energy neutron, and as you increase the amount of moderator, what I mean is you go deeper in the center, the response is moving forward to larger energy neutron. The importance here, they include a shell here that increase the response for large energy neutrons. You can notice here is 10,000 MeV neutrons. Well, this is another design in which is a 30 centimeters diameter polyethylene sphere having 19 pieces of lithium-6 and 1 piece of lithium-7 glass scintillator detectors that are in this array, and they present here the different response function for the detectors allocated inside the sphere. And another approach is, instead of using a sphere, you change a cylinder that has, in this case, 7 gold foils, and you bombard the spectrometer by this in this phase, and each gold detector has a different response that you can see here. As you go deeper, the response is moving forward to larger neutrons. When you have very near to the surface, the response is larger for low energy neutrons. This is a paper published by Turnisak in last year. 2023, in fact. And this is the last design I'm going to show you. This is Diamond, which is a direction-aware isotropic and active neutron monitor with spectrometric capabilities. In fact, it was designed like a neutron area monitor, but also has a possibility to use this device to obtain the spectrum. So it's a polyhedron. The polyhedron was designed, it tried to mimic the spheric and to machinate, to make the pieces all together like a sphere. And inside this, they put a matrix of semiconductor thermoneutron detector, which are based in lithium-6. And despite of the recognized potential, the use of binary spheres in routine activity is strongly hindered by practical limitation. One is the need of a sequential exposure of each sphere. The other is the need to have a response matrix. The other is the need to unfold procedure, to use unfolding procedures that you take the signal of your detectors and you calculate with these values the spectrum, which is a complex problem because it's an ill-conditioned algebraic problem. So you need a way to solve this problem. Eventually the resulting spectrum will have a low resolution, and the other drawback of using the binary sphere spectrometer or any other device similar or based in the principle of binary sphere spectrometer is the system weight. In order to enhance the technological independence, it's important to design and build a neutron spectrometer. So the objective of our work was to estimate the neutron response of a novel passive spectrometer using Monte Carlo methods from 10 to the 9 up to 20 MeV neutrons. The spectrometer is made with 11 polyethylene regular parallelepipeds with 2 pairs of thermoluminescent dosimeters, 2 TLD600 and 2 TLD700. In addition, was estimated by very first time the absorbed dose response due to neutrons and gamma rays in each TLD. These gamma rays come during the interaction of neutrons with the polyethylene nuclei, which are carbon and hydrogen. You can produce 2 MeV and 2.2 and 4.4 MeV photons or gamma rays due to the neutron capture in hydrogen or due to the inelastic scattering with carbon and due to the neutron absorption in hydrogen. So during the interaction of neutrons with your moderator, you will produce gamma rays that are absorbed by your the TLDs, and it's important to know the energy absorbed, the dose absorbed by your devices. Okay. So that's why we included these responses. How we did it? Well, we used the principle of use pairs of TLDs to measure thermal neutrons. It was published by us in 2002, and we have the equation. You only need to have the readout of the TLD 600, the readout of your TLD 700, and you evaluate the experimental value of your K, and the single difference in between the readouts of these types of dosimeters give you the net neutron signal that you need to calculate your neutron spectrum. We use the MCMP 6.1 code. In the model, we include our thermal detector pairs of TLD 600 and 700 ray bond type with these dimensions, and the moderator was polyethylene, high density polyethylene, and we use 6 regular parallelepipeds. We make six arrays, like our spectrometers has six pieces, and the tallies, we include the response in each TLD 600 and 700, and the response was this nuclear reaction with lithium-6 per each Newton square centimeter that arrives to the array. And we also include the absorbed dose due to neutrons and gamma rays in each TLD. Finally, the response was the average of the 2 TLD 600 and the 2 TLD 700, and the response to the absorbed dose was the average of the 2 TLD 600 and 2 TLD 700. So here are the 6 arrays, 2, 4, 6 arrays, in which is a piece of polyethylene with these dimensions. In the center are the 4 TLDs, 2 TLD 600, 2 TLD 700, and the fifth array has the 0.5 thickness, and we calculate the function response. Then we add 2 other plates, 2 other regular parallelepipeds having 2 centimeter thick. Now our array has 4.5 centimeter thick, and so on. We add another 2. We have the array with 8.5 centimeters thick, 12.5 centimeters thick, 60.5, and 20.5. When we arrive to this array, we have a cube. Our spectrometer becomes a cubic. It has a cubic form. Well, I want to present you our results. Our results are this is the response, the number of lithium-6 the number of reactions having neutrons with the lithium-6 producing alpha particle and tritium per each neutron by square centimeter that arrives to the array. This is the matrix response, the average of the matrix function in TLD 700, and this is the average of the matrix function of the TLD 700. As the neutron energy increases, the tendency of both responses tend to decrease. But I want to emphasize the difference between the response of TLD 700 and the TLD 600. Notice here that it's a 1, 2, 3 orders of magnitude in the difference here, and we come here is 1, 2 orders of magnitude. So now I'm going to present you the these two response functions when we increase the thickness of the array. Now this is the RP is 4.5, and you can notice that the response begins to be modified, but regardless, the modification looks similar for both types of dosimeters, being larger for TLD 600 in comparison with TLD 700. And so on for the rest of the arrays. When we increase the thickness, the shape it keeps, the orders of magnitude remain almost constant, but it's changing the response function. We increase now at 12.5, we increase now to 16.5, we increase now to 20.45, and we can notice that the larger response has moved to the larger energy neutrons. Well, if we put all together the response function, particular for the TLD 600, well, we have the matrix response for the regular parallelepiped spectrometer. If you recall, one of these response functions that I show you in the published papers almost have the same shape. Here it looks very similar to the cross-section of lithium-6, and as you can notice, as you increase the amount of moderator, the function is moving to the larger energy neutrons. Here for low energy neutrons is the Baer detector, where we have a very small amount of moderator, and as we increase the amount of moderator, the response diminish, but the maximum is moving to high energy neutrons. What we are looking is to design a device that the different functions, when we add all the function in a single function, we would like to have a single line here, a straight line, meaning that if my apparatus could have this behavior, means that they have the same efficiency to detect any neutron regardless the energy of the neutron. Now I'm going to present you the matrix response, and I'm going to include now the total function. And you can notice that the total function is almost a constant function. Okay. Well, now I want to show you the response of both types of TLDs to the absorbed dose due to gamma rays. And you can notice for the first array, which the thickness is 0.5, the response of both TLDs is the same, regardless if it's 600 or 700. On the other hand, for the absorbed dose due to neutrons, the response is very different. It keeps more or less or approximately 1-2 orders of magnitude. Here, as you move to a larger energy neutrons, both responses, the capability of absorb those due to neutrons, as the energy neutron increases, both dosimeters tend to have the same response. This is the thinner array. This is the larger array, the 20.5 array, and you can notice that the shape is now changed, but good morning, dear colleagues. The polyhedron was this is the last design I'm going to show you. This is diamond, which is a direction-aware isotropic and active neutron monitor with spectrometric capabilities. In fact, it was designed like a neutron area monitor, but also has a possibility to use this device to obtain the spectrum. So it's a polyhedron. The polyhedron was designed tried to mimic the spheric and to machinate to make the pieces all together like a sphere. And inside this, they put a matrix of semiconductor thermal neutron detector, which are based in lithium-6. And despite of the recognized potential, the use of binary spheres in routine activity is strongly hindered by practical limitation. One is the need or a sequential exposure of each sphere. The other is the need to have a response matrix. The other is the need to unfold procedure, to use unfolding procedures that you take the signal of your detectors and you calculate with these values the spectrum, which is a complex problem because it's an ill-conditioned algebraic problem. So you need a way to solve this problem. Eventually the resulting spectrum will have a low resolution, and the other drawback of using the Bonner sphere spectrometer or any other device similar or based in the principle of Bonner sphere spectrometer is the system weight. In order to enhance the technological independence, it's important to design and build a Newton spectrometer. So the objective of that I show you in the published papers almost have the same vector where we have a very, very small amount. Any Newton, regardless, for the absorbed dose due to neutrons, the response is very different. It keeping more or less or approximately 2 orders of magnitude. Oh, here, as you move to a larger energy neutrons, both responses, the capability of absorb those due to neutrons, as the energy neutron increases, both dosimeters tend to have the same response. This is the thinner array. This is the larger array, the 20.5 array. And you can notice that the shape is now is changed. But for 4TLD, the response is the same, but for neutrons, the absorbed dose is very different. Well, as conclusion, we want to say that a novel passive Newton spectrometer was designed and the matter response was estimated using Monte Carlo methods. The spectrometer is 10 polyethylene parallelepipeds with these dimensions and 1 polyethylene parallelepiped with this dimension where 4 TLDs are hosted to 600 to 700. The response function was calculated for neutrons from 10 to the minus 9 up to 20 MeV neutrons. It was estimated for the 6 arrays. In addition, the absorbed dose due to neutrons and the induced gamma rays was estimated in the TLDs. Therefore, the conclusion is that due to the difference in the concentration of lithium-6 in TLD 600 and 700 for each array, the response function is between 2 and 3 orders of magnitude larger for TLD 600 in comparison with TLD 700. The absorbed dose due to neutrons in TLD 600 is approximately 2 orders of magnitude larger to the Newton absorbed dose in TLD 700. On the other hand, the absorbed dose due to gamma rays is the same in both types of TLDs. Therefore, the thermal neutron signal can be obtained by the difference between the TLD 600 readout and the TLD 700 readout. The matrix response looks alike to the matrix responses of multi-moderator or single moderator spectrometer, regardless the moderator material and the type of the detector. And our design, our spectrometer, is only weighs 8 kilograms. So with this, I want to thank you for the generosity of your attention. Here is my email if you need to contact with me. And I want to congratulate to the King Saud University for hosting this important meeting. And I want to congratulate to the IRPS for the 40th anniversary. Thank you very much and enjoy the meeting.
Assalamualaikum warahmatullahi wabarakatuh, and very good morning. Thank you for having me speak at IRRMA12 2025. It's a great pleasure. I'm here to share our presentation on some of the work we've done in fiber optics dosimetry system, particularly tailored for flash radio therapy. A bit of introduction. Our team is from MMU, in particular the Fiber Optics Research Center, where we focus on design, fabrication, characterization of specialty optical fibers with various applications. And I guess in this particular presentation, we'll be interested in sensing applications. We have several facilities, including fabrication and characterization facilities, and also work related to simulation and modeling. We're a small group of professors and postgraduate students working together. Now, the work that we are presenting today is centered on optical fibers that's being used for real-time sensing of ionizing radiation, and in particular, we'll be talking about flash radiotherapy today. But a bit of a background: optical fibers are very small, with 125 micrometers diameter. It is possible to go down to 125 or even less. So the search for a new material with good sensitivity, robust and high spatial resolution, and impervious to water in particular, has led us to working with optical fibers as a scintillator used for real-time sensing of ionizing radiation. So with very good high spatial resolution, being impervious to water, and because of the fabrication facility that we have, it is possible to tailor the sensitivity or applications in particular with the use of the fabrication facility, namely MCVD. That has led us to work collaboratively in the study of silica host or silica based optical fiber dosimeters, whether they are doped or undoped and coming into different shapes or geometries, different dopant concentration, different types of dopants, etc. And this was possible, and we started work in 2015 collaboratively with few agencies, few universities, Nuclear Malaysia, Telecom Research, University of Surrey, UKM, UITM, UPM, UTM, and University of Malaya. That collaborative project had led us to, we started work with thermoluminescence, but later on moved on to radioluminescence and optically stimulated luminescent dosimetry system. So we came up with a real-time optical fiber RL/OSL dosimetry system using germanium doped optical fiber scintillators, which was coupled to a PMMA fiber cable as a conduit or as a waveguide, delivering the radioluminescence to the photomultiplier tube detector. We were capable of measuring both dose and dose rates with variable gating time from as low as 1 microsecond, and having a maximum count rate of 10 to the power of 6 counts per second. Now, this is a typical measurement setup in a radiotherapy facility. Yeah. So in our earlier works, we had worked with University of Science Malaysia in its Advanced Medical and Dental Institute or Research Institute with the LINAC beam producing the beam, the ionizing radiation, right onto the fiber optic scintillator, with the radioluminescence being produced. The radioluminescence signal travels along the optical fiber, and at the photodetector, a photon counting mechanism with the use of a counting unit is able to count the number of photons produced through the radioluminescence and being recorded and later on analyzed with an attached computer. Now, this is typical response of an electron and photon beam at various dose rates. In this case, we were exposing the optical fiber scintillator to 6 MV photon and 6 MeV electron, which we reported earlier. Now we moved on to work on time resolved dosimetry, and this is getting more towards the flash radiotherapy measurements. We were working on high dose radiotherapy applications, potentially up to 40 grays per second. But at this point, we did not have any access to a flash facility. But we had worked on several types of scintillators which would be suitable for time resolved dosimetry. The scintillators were fabricated by our partners and ourselves. We had the germanium doped silica, which was by MMU, and we had cerium doped silica through solution doping produced by our partners in India, the Central Glass and Ceramic Research Institute. We had 2 scintillators produced by our partners in Shanghai University, the key laboratory of specialty fiber optics and optical access networks in Shanghai University, one being the cerium doped DX crystal derived silica fiber, and another is the cerium and terbium doped DX crystal derived silica fiber. So with this time resolved capable scintillators, we were able to make these measurements. If you look on the left, this is a time resolved output signal coming from a cerium terbium co-doped DX scintillator. This is after being exposed to a 10 MV dose rate, 100 centigrade per minute, fixed dose of 50 centigrade with a gating time of 100 microseconds. So you can see that we are able to zoom into the single pulse, and we can measure the width of the pulse using a digital oscilloscope. And on the right, you can see a pulse train, which can lead us to the measurement of the pulse repetition frequency. Now, zooming into the pulse, we would then be able to measure parameters such as the rising time of the pulse, the decay time, and we analyze the decay time and the rising time to be a composite of the phosphorescence decay and also the capacitive and inductive effects of the entire system. So with this kind of resolution, we would then be able to, zoom in and hence deliver a time resolved dosimetry analysis. We later on attempted to analyze further the single pulses at various energy, and we can further analyze pulse substructures as reported earlier by Isodori in 2021. If you look on the left, there's an example of a pulse substructure which was reported earlier. And using the optical fiber scintillators, in this case, germanium doped fibers, we were also able to zoom into the pulse substructure, giving some insights into the power delivery system of the LINAC behavior. Now, moving on to the core of the presentation. So with that capability, we were given the opportunity to work with Tsinghua University a center or a lab that was working on linear accelerators, or essentially accelerators for high energy electron beams, and they were working towards flash radiotherapy. In this case, we had brought our RL or radioluminescence dosimetry system to measure ionizing radiation in tandem with the flash radiotherapy or LINAC system at Tsinghua University. So we had used a germanium doped silica optical fiber scintillator, and in comparison or for reference, we had used a radiochromic film for calibration and reference purposes. The LINAC you can see on the right is a simple electron beam that had then been exposed to the beam was then delivered to the scintillator. If you look at the diagram on the bottom, yeah, and these are the experimental parameters. We had used 6 MeV, so hence there was no filter being used actually, and the pulse width was 4 microseconds with an instantaneous dose rate of 500 kilograys per second. And we exposed the scintillators to several pulse repetition frequencies ranging from 300 Hz all the way down to 50 Hz. And we had also measured at various doses ranging from 10 gray all the way up to 50 gray. So this was the scintillator used. It's a germanium doped silica fiber with the cladding diameter, core diameter, germanium concentration, and on the right is a elemental analysis of the optical fiber scintillator. Yeah, and these are some of the results that we obtained. This was for 6 MeV at 50 gray delivered with a pulse repetition frequency of 50 Hz. Yeah, and the three diagrams are essentially the same, but we are zooming in. If you look on the left is the full view. In the middle is an extended view of it, the same train of pulses, and the one on the right is one which is zoomed into the pulse. We show here also another set of results for 10 gray. You can see that the number of pulses is reduced. This is at PRF or pulse repetition frequency of 50 Hz. Yeah, and we then delivered 10 gray, but this time with a PRF of 100 Hz. Again, you can see the pulse train and the number of pulses delivered for different dose from 10 gray to 50 gray, and the spacing you probably observe the spacing between the pulses at lower PRF at 50 Hz, and this is at 100 Hz. So what we see here with 100 microseconds gating time, the PMT accumulates the RL counts over that gating time, and we observe subsaturation within this gating time. In particular, the PMT's count linearity which would limit the counts per gate to roughly about 1,600 counts. So you can see in these two traces, whether it is 50 gray or 10 gray, the peak count is saturating at 1,600 counts per gate. Yeah, and this is imposing some form of limit, some form of saturation to the measurement. But nonetheless, you'll see the pulse shape is not being truncated. I mean, doesn't have a truncating behavior. So we believe that this is almost at the peak, and with the kind of dose that is being delivered, there will be some error in measurement, as I will show you in a while. As far as the dose delivery mechanism is concerned, you'll see that higher doses means more pulses are being delivered at the dose rate of 50 kilograys per second. And you'll see that the RL response per pulse remains consistent, but the number of pulse increases with the dose. Another observation we can see here is in terms of the pulse repetition frequency. At 50 Hertz, pulses are well separated, and that would ensure better RL measurements with no pile up, because there's enough time to decay between the pulses. At higher pulse repetition frequencies, we see some overlapping of the RL signals in comparison to the diagram to 50 Hertz, for example. And you see that there's lesser time for the pulses to decay between the pulses. And this imposes a challenge at high dose rates, where you see some form of saturation at high doses or higher PRF that impacts linearity and accuracy of the RL measurements. This is due to the potential pulse pileup observed at higher pulse repetition frequencies. And having said that, some of the considerations that we suggest at this point would be to use shorter gating times or PMTs with higher count linearity limits. Yeah, and on top of that, if you are still using one which has some form of limit, correction factors needs to be applied to address these deviations, especially at high doses or at high pulse repetition frequencies. We further analyze those train of pulses where the area under the curve were integrated over time to assess the total RL count. This is one which we analyzed the total counts with respect to increasing dose, and we can see a good linear response between the total counts versus the dose being delivered, a linear response R squared of 0.9994. And in this particular case, it is done at a PRF of 50 Hertz. Yeah. Then we analyze the same for a higher PRF at 300 Hertz. To the naked eye, it might seem to be linear, but you can observe from the value of the R squared, which has now reduced to 0.9957. So the linearity has somewhat reduced, and the slope of the linearity, the response has also reduced in comparison to the earlier analysis at 50 Hertz. Yeah. So we've carried out the same analysis now for all the pulse repetition frequencies between 50 Hertz to 300 Hertz, and we can observe here, although the linearity is somewhat maintained, the slope for different PRF has reduced as the PRF increases, and this again, as I suggested earlier, indicates some form of pulse pileup as the duration between the pulses reduces when the PRF increases. And again, I highlight the linearity measured through value of R squared is also reducing as the PRF increases, indicating the need to have some correction measures. The same analysis was then carried out in a different way. This time we looked at the increase of dose from 10 gray to 50 gray, and at higher PRF we see the recorded counts appear to drop due to pulse pileup again, as the duration between the pulse reduces when PRF increases. We also observe that the PRF dependent behavior is much less at 10 gray when you compare to 50 gray, due to the higher number of counts, and the impact is seen to be more obvious at higher doses. Now, some further discussion I think we can have here is to look at the effect of PRF is visible between 50 Hz to 300 Hz, as you can see in the diagram on the right, showing you 10 gray delivered at 5 pulses, delivered with a PRF of 50, 100, and 200 Hz. And we can, when we analyzed it further, increasing the PRF from 50 Hz steps, the subsequent total counts decline, as shown, by 4.4%, all the way down to 15.6% for 100 up to 300 Hz respectively. So the increasing percentage of decrement here is due to the more intense segments of the emission between the cutoff of higher PRFs. Since the emission follows an exponential decay, the shorter time between the pulses truncate the radioluminescence through the exponential decay. We also overlap the traces, if you can see from the left, on the left. This is for a 10 gray with 5 pulses delivered at 50 Hz, and another one at 20 gray, double the dose, with 10 pulses delivered at 100 Hz. So the overlap traces here show that the germanium doped optical fiber scintillators recovers between the measurements, as the first pulse overlaps completely for different exposures. And now, however, you can also see the following pulses during the same exposure, which is as close as 3 milliseconds apart, governed by the PRF, are affected by a memory effect, and this is due to slow phosphorescence from earlier emissions. And the net effect, as more pulses are added at higher PRF, causes more cumulative signal intensity from the pulses at any given time. So, with the results that we report today, I'd like to conclude by highlighting that the germanium doped silica optical fiber scintillator used has some limitations, but nonetheless it has advantages which are still prevalent, especially in its ability to measure remotely, real-time, with pulse-by-pulse analysis, leading to potential use in flash radiotherapy, quality assurance, calibration, and radiation protection. Now, the limitation in terms of its linear response, as earlier pointed out, as the PRF increases with higher doses, can somewhat be addressed by introducing a correction factor, or by further improving the scintillator itself and how the measurements are being done by using a much higher count linearity PMT, for example. Yeah. So with that, I'd like to thank all our listeners today, and I'd like to also thank all our collaborators. Yeah. As pointed out here, we could not have done what we present today without all their support, and particularly in this case for flash radiotherapy, we had worked with Tsinghua University, Beijing, China. Thank you so much for your attention. This is the team, me and the team. We were working in USM, in University of Science Malaysia in Penang earlier.
Assalamualaikum and good afternoon, everyone. My name is Nur Hayati Abdullah from University Putra, Malaysia. Topic of my presentation is the use of fabricated germanium doped optical fibers and TLD100 in the preliminary small field photon dosimetry audits. These are the contents of my presentation. Let's start with introduction. What is the significance to conduct small? My name is Nur Hayati Abdullah from University Putra, Malaysia. Topic of my presentation is the use of fabricated germanium doped optical fibers and TLD100 in the preliminary small field photon dosimetry audits. These are the contents of my presentation. Let's start with introduction. What is the significance to conduct small field dosimetry audits? Advanced radiotherapy methods such as IMRT provide highly accurate tumor targeting with varying intensity of radiation with the objective to minimize damage to the surrounding healthy tissue. However, these complex methods come with increased risk due to their sophisticated nature and also the use of high radiation doses. Therefore, the small field dosimetry audits require more comprehensive and stringent process, such as verification of the accuracy of dosimetric measurement, validation of the performance of the treatment planning system, and also comparison of the output factor. Next, why we choose fabricated germanium doped optical fibers and TLD100 powder as a transfer detector. Many studies show that this type of detector has excellent dosimetric characteristics, especially in terms of linear dose response, energy independence, and also durability after repeated use for the radiotherapy dosimetry application. Furthermore, the small physical size of optical fiber make it useful for eliminating the volume averaging effect and also perturbation effect in the small field dosimetry optic. The optical fiber also are non-hygroscopic, convenience of use, and reasonable cost because it is manufactured locally in Malaysia. Meanwhile, the TLD100 powder is a well-established dosimeter and has been used for a large-scale dosimetry audits by the IAEA and also IRRMA in the USA. There are two objectives in this study. The first one is to establish dosimetric characteristic and associated correction factor of fabricated germanium doped optical fibers and compare them with the TLD100 powder for use in the small field dosimetry audits. Second, we will conduct a preliminary small field photon dosimetry audits in evaluating the accuracy of absorbed dose and also to measure the dose distribution profile performed by the treatment planning system. Methodology. There are 6 characteristics of the study. The first one is dosimeter sensitivity, dose responsiveness, beam energy dependency, signal failure over time, dose rate dependency, and also field size dependency. So this picture shows the irradiation setup for the photon beams at 100 SST and 10 cm. During the dosimetric characteristic, the dosimeter was placed inside this BMNA slab phantom with a slot to accommodate a single capsule of TLD100 powder or fibers to reduce the air gap between them. From this characteristic, we will establish the relevant correction factor to calculate the measured absorbed dose from the dosimeters using this established equation. Then we will conduct the small field dosimetry audits. In this audit, the participants were requested to calculate the number of monitor units required to irradiate the dosimeter at 10 cm depth, 100 SSD to 2 gray to the dosimeters, TLD and also optical fibers, and 8 grays to the EBT3 films, according to the GPS. For the different field size, from 10 by 10 cm, 2 x 5 cm, and 2 x 2 cm for 2 beams 6 and 10 MV. So these are the irradiation setup for small field dosimetry audits. We do the irradiation in water using the custom-made holder that we use for the fibers and TLD, and also this is the holder for the EBT3 film. Result and discussion. Before dosimetry characteristic, approximately 400 fibers, cylindrical fibers, and also 400 flat fibers were screened to ensure the use of equivalent sensitive dosimeter. This figure shows the distribution of each TL signal from a single fibers normalized to the mean TL signal of all fibers for both types. In order to reduce the uncertainty that may arise from the sensitivity correction factor, we group this sensitivity within the plus minus 5% by comparing the individual signal to the mean. From this fiber, then we group into 16 fibers per capsule to obtain a group sensitive correction factor as shown in this figure. This is the result of TL signal per unit mass versus absorbed dose for the TLD 100 powder, flat optical fibers, and also cylindrical optical fibers. The results show that all three detectors have an excellent interval of linearity within the range of 1 gray to 3 gray, with the determination coefficient is almost 1. We also check for the mean sensitivity, which is the ratio between TL signal per mass per gray, and the results show that the relative standard uncertainty for this sensitivity is less than 0.51%. From this result, we produce the linearity correction factor that will be applied in the absorbed dose calculation using this equation. The regression analysis revealed that there has a significant difference between absorbed dose and the linearity correction factor. Therefore, it is very important to do this correction in order to enhance the accuracy of the dose calculation. In terms of beam energy dependency, all dosimeters exhibit a high energy dependency, particularly at higher beam energy of 15 MV. Therefore, careful consideration of correction factor for each beam energy is essential due to the significant impact.
Assalamu alaikum. Hope all of you are well. At first, I'd like to give my gratitude to Allah, because without His wish, it's not possible for me to give my speech in this prestigious stage of 4th International Forum on Advances in Radiation Physics. And then, I'd like to express my gratitude to the authority who gave me the permission to talk here. Last but not least, I am honored to get this honorable audience here. Now I am going to talk about an innovative glass system which has shown good radiation shielding ability without toxicity, having tellurium dioxide, a key factor on this glass composition. Outlines of these presentations are introduction, research objectives, materials and methods, result of discussion, and finally, conclusions. Research objectives. To invent new glass system, which will have good radiation shielding ability without toxicity. After that, among the studied glass composition, to find out which composition will show the best shielding ability against radiation. As you know, lead has the best shielding ability, but the most unwanted thing is that lead is toxic. In this research, we are trying to show tellurium dioxide playing a crucial role to increase the ability of radiation shielding for the interest of replacement of lead because of its toxicity. Though radiation has severe adverse effect, yet it's unavoidable for us to deny its important use in some crucial activities for our daily life. For instance, medical research, agriculture, power plant, and so on. Hence, considering its pros and cons, researchers come into a decision to minimize the exposed limit of the radiation. That means we have to follow the proper radiation protection rules. According to Thumb's rule, the radiation protection rules for minimizing the effects of hazardous radiation. Rules number 1, try to spend shortest time beside the radiation sources. Number 2, hold the long distances from the radiation sources. And number 3, to use adequate radiation shielding materials according to the strength of the radiation sources. Considering the 3 rules of the thumb rules, researchers are giving their highest effort to invent the best radiation shielding material. We know the traditional shielding materials are lead, concrete, glass, epoxy, polymer, etc. Every shielding materials have few merits and demerits. According to our necessity, we have to choose required one. For considering numerous advantages, now in our research, we have chosen glass materials because of its few advantages like lightweighted, transparency, moisture effect freeness, having no toxic element, less contamination with the environment. To produce our desired glass, a few ingredients such as boron trioxide, tellurium dioxide, bismuth trioxide, zinc oxide, and calcium oxide have been mixtured according to their considered estimation. The ratio of those ingredients will be shown in the next slide. Now, for manufacturing these glasses, those following steps have been maintained. At first, to produce high purity stoichiometric mixture oxide, in a 20-gram batch, all the ingredients have been mixed first. Then for making a homogenized powder, an agate mortar was used to bleed the mixture. After that, for applying the melt quenching technique, and the mixture were put into an aluminium crucible. Place them in an electric furnace. Next, the melt were put into a stainless steel mold. After that, for anneal them at 400 degrees centigrade temperature for 3 hours. Then we get our desired manufactured glass. After getting our desired glasses, using HPG detector, radiation shielding parameters have been measured. Now, these are the ratio of the studied glass compositions. Here it has been shown that the ratio of the bismuth trioxide and zinc oxide are fixed. The variation has been followed among the boron trioxide, tellurium dioxide, and calcium oxide. 4 samples have been manufactured using the ratio of the glass components presented in this table. After completing the manufacturing, the picture of the glass samples were like this. Because of various glass compositions, the density of the glass samples were different. At a glance, we can see that it has been found that sample tellurium 15 calcium 20 has shown the highest density. lowest density 4.070 gram per centimeter cube, whereas sample tellurium-30 calcium-14 has represent the highest density 4.498 gram per centimeter cube. To identify the radiation shielding capability, there are few parameters we have seen that, such as linear attenuation coefficient, half value layer, transmission factor, effective atomic number, etc. Using the HPG detector, the incident and transmitted photon intensity can be measured. After that, using those formulas, the value of shielding parameters can be calculated by the value of incident and transmitted photon intensity value. Now, I am going to discuss about the shielding parameters of the studied samples, and then we will finalize the conclusion. Now, results and discussion. This graph represents the density versus linear attenuation coefficient. From this graph, it has been clear that sample tellurium-13 calcium-14 show the highest value of linear attenuation coefficient, which is 0.685 centimeter inverse approximately, whereas sample tellurium-15 calcium-20 shown the lowest value, 0.615 centimeter inverse approximately, at energy 0.344 mega electron volt. However, at the same energy, samples shown the similar trend for the effective atomic number. Here, it is clear that glass samples with highest density shown the highest value of linear attenuation coefficient and effective atomic number. This graph illustrates the energy versus transmission factor. Here, sample tellurium-15 calcium-20 and sample tellurium-30 calcium-14 have been chosen for this measurement. For these glass samples, numerous thicknesses glasses were prepared, such as 0.25 centimeter, 0.5 centimeter, 0.75 centimeter, and 1 centimeter. For this graph, it has been found that at energy 0.122 mega electron volt, sample tellurium 30 calcium-14 with the thickness of 1 centimeter presented the lowest value of transmission factor. You know, the value of lowest transmission factor has been considered as a good radiation shielding materials. In that sense, we can say that tellurium-30, calcium-14 is the best, showed the best radiation shielding ability. This graph represents the thickness versus radiation protection efficiency. It depicts that at energy 0.122 mega electron volts, sample tellurium-30 calcium-14 shown the highest radiation protection efficiency value for the thickness of 1 centimeter. Conclusion. Considering the value of all measured shielding parameters, it has been found that started glass samples tellurium-30 calcium-14 showed the best radiation shielding ability among the started glass samples, having 31 mole% of boron trioxide, 30 mole% of tellurium dioxide, 5 mole% of bismuth trioxide, 20 mole% of zinc oxide, and 14 mole% of calcium oxide. In addition, to analyze the started glass samples composition, it has found that the highest amount of tellurium dioxide enhance the radiation shielding ability of the considered glass samples. Thus, we can say that tellurium dioxide works as a key factor for increasing the radiation shielding ability of considered glass samples. Thanks, all of you.
Good afternoon, everyone. I'm Hao Ding from Tsinghua University. It's my great honor to attend this IRRMA12 conference and to share about our recent work about evaluation of nanoparticle dose enhancement by inverse competence scattering source using Monte Carlo simulation. I'm gonna divide my talk into 4 parts. The first part is about introduction. As we all know, cancer treatment is always one of the most concerned topics for the biomedical engineering, and radiotherapy is the most common treatment method. To improve the efficiency of radiotherapy in the last decade, researchers started to use nanoparticles to enhance the radiotherapy. It's easy to understand when a nanoparticle is injected into the tumor cell. The nanoparticle with large cross-section could react more with X-ray and gamma ray, and therefore lead to more energy deposition and more redox species productions. Certainly, with different property of nanoparticle, the performance are various. Different energy X-rays have different enhancement effects between macroscopic and macroscopic levels. However, the common use X-ray tube and linear accelerator have a broad energy spectrum. Therefore, there is a need an energy tunable and monochromatic source to meet the requirement of optimal radiotherapy performance. Synchrotron light source, inverse Compton scattering light source, and X-ray free electron laser light source are different types of advanced light source which could meet the requirement. The basic theory behind the beam production facilities are slightly different. As time is limited, I'm not going to talk about all this here in details, but we can see from this comparison figure that ICS sources have the high and wide energy range with a relatively high brightness. In Tsinghua University, we have focused on the inverse Compton scattering light source for over 20 years. It uses the collision between high energy electron and laser, so the energy is transferred from the beam to the photons. Therefore, we can obtain high energy photons. The energy range of ICS source could cover X-rays and gamma rays, which are generally used in biomedical engineering. We built TTX facility 50 years ago covering 20 to 50 kUA, and we are currently constructing the Vegas facility covering 0.225 MUA, and will finish in this year. So the video shows the constructing progress through this year. The accelerators has been already fully assembled and ready for producing photons. So in this term, Vegas is extremely suitable for medical imaging and radiotherapy, as this energy is usually for the gamma knife to kill the cancer. Worldwide, there are several ICS sources for medical applications specifically for different types of radiotherapy. Tomax brought out the idea of stereotactic radiotherapy. MUCLS focused on the microbeam radiotherapy, and BRIAX simulated rotational radiotherapy with a good performance. So in our lab, we propose using the ICS source for nanoparticle enhanced radiotherapy, using the properties of monochromatic energy, continuous tunable energy, and small focus. To promote the feasibility of ICS source for nanoparticle enhanced radiotherapy, we have made some simulation to simulate the physical process and the chemical process. So the second part, I will talk about the simulation model we set up. The open source Monte Carlo package Gen 4 toolkit was used to create and perform the multi-scale nanoparticle enhanced radiotherapy model in our study. The configuration and geometry of the multi-scale simulation model is shown in this figure to mimic the real radiotherapy conditions. This multi-scale model was composed of two steps, macroscopic step and the macroscopic step, and four submodels including the incident beam model, body model, tumor model, and cell model. To achieve the transition between these two steps, phase spaces were acquired at selected regions, the front of the tumor model, and in this body model to score the properties of the beam, including the particle type, momentum energy, and directions. Specifically for the beam model, the ICS sources are quite different compared to the normal X-ray tube. X-ray tube is based on Bramler, so it has a continuous spectrum. The characteristic peak of this spectrum is the excitation of fluorescence of target material. While ICS has a quasi-monochromatic energy and follows Gaussian distribution, Therefore, it has a better homogeneity, and this homogeneity is largely depending on the energy and bandwidth divergence. For the macroscale simulation, the photons are modeled to represent the body, which are composed of a normal tissue, tumor, and a normal tissue in row along the beam directions. The thickness and depths could be varied to represent different conditions. The nanoparticle is injected into the tumor region for the enhanced radioseparate simulation. And at the specific interest regions, the phase spaces of incident particles are recorded for further macroscopic simulations. For the macroscopic step simulation, due to the finite memory, it's infeasible to construct the whole tumor block with the multiple cell structure. Instead, a cubic tumor model with a side length of 200 micrometers located at two selected regions with the tumor block was constructed and analyzed. The tumor model was fully occupied with a total of over 1,000 spherical cells, which were arranged in a cubic closed package structure. The cells in the tumor model were set as spheres with radius of 10 micrometers. Each cell contains a spherical nucleus with a radius of 3 micrometers in the center, and the space outside the nucleus was defined as a cytoplasm. Both the nucleus and the cytoplasm were initially composed of pure water, and nanoparticles were imported into the proper region of the cell model in two configurations. In the first configuration, the nanoparticle was designed as a spherical shell with a thickness of 21 nanometers, coating the surface of the nucleus of each cell. Where in the second configuration, nanoparticle was assumed to exist evenly in the cytoplasm, clustering as smaller spheres with radius of 100 nanometers. So by conducting this simulation, we can get the results of the multi-scale simulation. The macroscope simulation result of the dose distribution without nanoparticle exhibits the cone-shaped pattern. The penetration depth at the edge region was smaller than that at the center due to the decrease of beam energy with the increase of angle. In terms of dose spatial distribution on the corner plane, the intensity distribution played a more important role compared to the energy divergence. The import of nanoparticle into the tumor block obviously affected the dose distribution in radial distance and depth. It exhibited a sharp peak at the tumor block and an enlarged cone pattern. The influence of four key factors, including radial location, nanoparticle concentration, tumor block thickness, and tumor block depth on the dose enhancement, was analyzed separately. The radial location and nanoparticle concentration have an effect on the homogeneity, and the different depths and thickness of the tumor block had no obvious impact. It demonstrated that SAS cells could fit different types of tumor and could change the beam property as required. For macroscopic simulation, the result shows that nanoparticle configurations have significant impact on the dose distribution in the cells. The different enhancement value for the macroscopic simulation and the macroscopic simulation in this study also reflect the influence of nanoparticle configurations. SAS source made the enhancement almost 1.5 times higher than the conventional 80 kV tube. With a bandwidth of 2%, it demonstrated a small trend with a energetic photons, which means it could have the same performance under the same conditions of synchrotron source. So when we go back to the fundamental physics process behind the energy deposition or enhancement, we can say it all depends on the generation of secondary electrons. We analyzed these electrons' contributions with different properties of nanoparticle. We found that alpha electrons contribute most at low energy and photoelectrons have relatively high energy. For different configurations, the energy deposition in the nanoparticle are quite different, leading to the variation of enhancement. Therefore, For different contents, it might need different nanoparticles, and the corresponding optimal energy is different. So the SL source with tunable photons could achieve the best enhanced radiotherapy. And this simulation platform we set up could also be used to guide the design of different nanoparticle medicines. So in the end, I'm planning to introduce our future plan. As medical imaging and radiotherapy could both be achieved by SAR source, and they have different optimal energy which could be realized by the SAR source as it could shift the energy. We are planning to combine these two functions, the diagnosis and radiotherapy, using our SAR source in the future. So this is pretty much everything I want to talk about today. Thanks for your listening.
Hello everyone. The title of this poster is Impact of Rare Earth Oxides on the Gamma Ray Shielding Feature of Borate-Based Glasses. In this work, we prepared different glasses with 3 rare earth oxides, and we study the radiation shielding properties of these glasses in wide energy range. In figure 1, we plot the samples, while in figure 2, we plotted the linear attenuation coefficient of the glasses as a function of the energy. As we can see from figure 1, the linear attenuation coefficient decreases with increased the energy, and the maximum linear attenuation coefficient is found at the lowest energy. And also we can see from figure 2 that the linear attenuation coefficient depends on the types of rare earth oxide, where the glass with ER203 show a higher linear attenuation coefficient than the other glasses. In figure 3, we plotted the linear attenuation coefficient and the effective atomic number with the energy. And clearly from this figure, we can see that the linear attenuation coefficient and the effective atomic number have a dependence on the energy, where change the energy causes a decrease in both parameters. And also from the figure, we can see that there are 3 types of interaction between the photons and the glass, and these interactions are photoelectric effect, Compton scattering, and pair production. In figure 4, we plotted the half value layer with the energy, and clearly the half value layer increases with the energy. And finally, in figure 5, we plotted the effective atomic number with the energy, and we can see that the effective atomic number has a notable variation or dependence on the energy, where the maximum effective atomic number is observed in the photoelectric effect region, while the effective atomic number show minimum values in the Compton scattering region. Finally, we can conclude from this work that the glass with or doped with ER203 has better attenuation feature due to the highest linear attenuation coefficient and effective atomic number. And thank you.
Hello everyone. The title of this poster is Effect of Zinc Oxide Particle Size on the gamma ray shielding ability of the 45 boron trioxide, 30 barium oxide, 25 zinc oxide glass system. New glass compositions including the 45 boron trioxide, 30 barium oxide, 25 zinc oxide system have been investigated, where S represents the zinc oxide particle size, micro, nano, and micro plus nano. The morphological characteristics and various size of zinc oxide particles were analyzed prior to the glass preparation process. 3 glass compositions of varying thicknesses were prepared using the melt quenching technique. Their shielding characteristics were experimentally evaluated using the narrow beam method with an high purity germanium detector, various gamma sources, and a lead collimator. The experimental linear attenuation coefficient at 0.059 million electron volt were 15.154, 15.483, and 16.032 centimeters to the -1 power for micro and nano and micro plus nano particle size respectively. The linear attenuation coefficient data were further used to calculate other radiological parameters, including the half-value layer, mean free path, and 10th value layer. Furthermore, the radiation shielding efficiency of the prepared glass materials was evaluated. The radiation protection efficiency of all 3 glass types was determined, revealing that the sample containing nano zinc oxide exhibited the highest radiation protection efficiency. The relative deviation among the nano, micro, and micro plus nano glass samples was also analyzed, highlighting differences in linear attenuation coefficient values, with the nano glass consistently showing higher values across all energies. The results suggest that nano-sized zinc oxide particles play a crucial role in optimizing the gamma ray shielding capabilities of porate glasses, underscoring their potential for advanced radiation protection applications. Thank you.
Hello, my name is Mu'min Taha Ahmed Hassan. I'm a senior physics student at Faculty of Science, Alexandria University in Egypt. My poster is about experimental study on borotellurite glasses, unveiling the radiation attenuation effects of barium oxide and erbium oxide. In this study, we used both of barium oxide and erbium oxide, each one alone, as a composite on the borotellurite glasses, so that we can check its attenuation effect and whether it's increasing or decreasing the efficiency of attenuation of the radiation. We used the radiation, a narrow beam of radiation from different energies of photons, and the results that we got were: we found a positive relationship between the linear attenuation coefficient and the concentration of erbium oxide, and we found an inverse relationship with half-value layer and the concentration of erbium oxide, and also an inverse relationship between the mean free path and the concentration of erbium oxide. While the last result was that there was an inverse relationship between linear attenuation coefficient and the energy of the radiation beam that was selected. So the conclusion that we found in the end was that there is a big improvement in the radiation attenuation performance of the prepared glasses as more erbium oxide is added, which was a good result and was expected. So this gives us another good way for multiple applications using the glasses as being a radiation shield for any place needs a wall of glasses, and any application needs radiation attenuation from glasses. Thank you.
Hello, my name is Mawadda Hashim, a fourth-year undergraduate student at the Physics Department at the Faculty of Science, Alexandria University in Egypt. The study is about gamma radiation shielding effectiveness of lead oxide doped borosilicate glasses, transmission factor, and attenuation analysis. In this study, the integration of lead oxide into a borosilicate glass system was investigated for enhanced radiation shielding properties. Glass samples with varying lead oxide concentrations in mole percent were prepared using the melt quenching method, as shown in the figure below. The density of the glasses increases from 4.579 to 5.044 gram per centimeter cube as a result of increase of the lead oxide content. The radiation attenuation factors were experimentally determined at 0.059, 0.662, 1.173, and 1.333 MeV using hyperpure germanium detector. The results indicate that increasing lead oxide content notably influences the mass attenuation coefficient and the effective atomic number. The 10th value layer increased significantly with rising energy levels. For the glass sample containing 31 mole percent lead oxide, the 10th value layer increased from 0.177 centimeter at 0.059 MeV to 5.325 centimeter at 0.662 MeV and to 9.094 centimeter at 1.333 MeV. Similarly, for the glass with 37 mole percent lead oxide, the 10th value layer increased from 0.146 centimeter at 0.059 MeV to 4.733 centimeter at 0.662 MeV and to 8.231 centimeter at 1.333 MeV. The results also showed that lead oxide has an inverse effect on the 10th value layer, where adding more lead oxide leads to decrease in the 10th value layer. At 0.662 MeV, increasing the lead oxide content from 31 to 37 mole percent reduces the 10th value layer by approximately 11.12%. The transmission factor for the glass with a thickness of 2 centimeters was investigated, and results showed that the transmission factor is nearly zero at 0.059 MeV, indicating that the glass provides complete shielding at this low energy. The transmission factor increases with rising energy, reaching 37.8 to 42.11% at 0.662 MeV, indicating that more photons penetrate the glass as the energy increases. Thank you very much.
Hello, my name is Dara. I'm a student in Environmental Studies Department in the Institute of Electric Studies and Research, Alexandria University. My research is about radiation shielding and waste recycling CRT glass in blister resin compost. At the first, this study evaluates a composed material composed of polyester resin combined with dry saturated with CRT glass for its effectiveness in shielding against ionizing radiation, particularly gamma rays. The research aimed to assess the activation and the mechanical properties of polyester resin composed in cooperating varying amount of CRT glass to evaluate their gamma ray radiation shielding effectiveness. The composed samples were prepared with varying proportion of CRT glass 0 to 50% mixed with polyester resin 100 to 50%. The linear attenuation coefficient ALC were measured with using the high field purity germanium HTGE semiconductor spectrometer. The experimental results were compared with the theoretical values for calculating using the PHI-X program, demonstrating the strong consistency between the two. In addition to the LAT, other theoretical parameters were calculated, including the mass attenuation coefficient, transmission factor, the best resulting performance. With the maximum mass attenuation capacity at the lowest energy level of 5, lighting is its sample attenuation capability. As shown from these figures, the radiation attenuation parameter of the composite sample were assessed by HPV detector and the different sources of energy. Due to the high composition of CO2 components such as lead oxide and barium oxide, which reflect the majority of incoming radiation, the studies conclude that incorporating CO2 glass improves the the study concluded that incorporating CO2 glass improves the shielding effectiveness of plastination against gamma radiation. This research holds promise for advancing waste management and electronic waste recycling while contributing to the development of easy materials for radiation shielding applications. The various radiation shielding applications were flexible and lightweight are required, such as medical, imaging, aerospace, and military settings. Thank you for listening. The radiation, particularly gamma rays. Thank you for listening.
Hello everyone, this is Isra Hassan Abdelgawad. I am a lecturer at Institute of Graduate Studies and Research in Alexandria University, Egypt. Here in this research, we focused on investigating the effect of neodymium oxide and barium oxide presence on radiation attenuation efficiency of a proposed boron-based glass matrix, and this is for radiation shielding applications. We prepared 4 glass samples with different concentrations of neodymium oxide and barium oxide by the well-known melt quenching method, and it is shown here in this figure. The attenuation parameters like half-value layer and radiation protection efficiency percentage were calculated based on the experimentally measured values of linear attenuation coefficient, and these were attained by the narrow beam technique, and it is shown here in this figure. The result obtained shown that increasing the concentration of neodymium oxide and barium oxide has increased the density of the prepared glass samples. Accordingly, an elevation or increase in the values of linear attenuation coefficient at different energy ranges were observed. Moreover, a decrease in the values of half-value layer by approximately 50% was observed at the 60 kilo-electron-volt range of energy. Furthermore, an increase or enhancement in the radiation shielding efficiency percentage was obviously observed at different energy ranges. Conclusively, we successfully synthesized a novel series of a boron-based glass matrix, and our findings revealed that increasing neodymium oxide and barium oxide in this boron-based glass matrix led to an elevation in linear attenuation coefficient values and accordingly increase or enhancement in the performance of the proposed glass matrix. Notably, our results recommend the promising neodymium oxide and barium oxide incorporation in different glass matrices such as silicate, telluriate, phosphate-based glass matrix. Finally, I'd like to thank you.
My name is Islam Mustafa Mbarak. I am a student at the Institute of Graduate Studies and Research, Radioactivity and Attenuation Efficiency of different ceramic samples selected from different countries. A study was conducted to evaluate the natural radioactivity of 7 ceramic samples selected from different countries and analyze their ability to reduce or absorb gamma rays. We analyzed 7 ceramic samples that coded from S1 to S7 using EDX analysis to determine their chemical composition as shown in Table 1 and Figure 1. Figure 2 shows the result of EDX analysis. We calculated experimentally linear attenuation coefficient for energy range from 0.06 to 1.33 million electron volt with a high priority germanium detector as shown in Figure 3, and also use XCOM software to calculate theoretical values for linear attenuation coefficient. And this linear attenuation coefficient data were used to compute other radiological parameters such as half value layer, mean free path, tenth value layer, transmission factor, radiation shielding efficiency. In Figure 4, linear attenuation coefficient demonstrated for ceramic samples. S3 sample consists of this chemical composition has the highest linear attenuation coefficient, and the S5 sample consists of this chemical composition. It's a list of them. Conclusion: the result shows that all samples reach the international safety standard. We observed that all the samples have difference in radiation shielding. This depends on density, chemical composition, heavy metal such as iron, potassium, calcium. The study emphasizes the importance of material composition and homogeneity to enhance radiation shielding. Further search could be directed to adjusting the material for better efficiency, but not at the expense of cost and sustainability. Thank you for your time and attention. It has been an honor to share my research with you here at the conference. I now welcome any question or discussion you may have. Thank you.
Good day to everyone. Today I'm going to present the finding from a study conducted at Phu Tinh General Hospital, Vietnam. It is implementation and validation of beam model for the electroscenery linear accelerator. We all know that external beam radiotherapy using linear accelerator is one of the most commonly used and effective methods for treatment a wide range of cancer. To achieve the optimal treatment outcomes, it is crucial to ensure accuracy between the actual treatment beam parameter in the treatment system and those in the planning software. So in this study, we focus on 6 MV and 10 MV photon beam. How did we do that? First one, for measurement, we use electron system, scenery system, and water phantom with a size 48 by 48 by 48 cubic centimeter to measure PDD and beam profile. The acquisition data process, we use the MyQA software. At the same time, on the Monaco software, we simulate the actual measurement process with a virtual phantom the size of 60 by 40 by 60 cubic centimeter. So all the data we got from measurement and data from export from Monaco software, we use for validation process. In validation process, we use Monaco Commissioning Utility, or we call MCU software. This software based on the gamma index methods to evaluate between the measurement and calculated data. Finally, we got PDD part rates, beam profile part rates, absolute dose comparison. And here I will show you some results. The first we take a look and we see the 6 MV and 10 MV is where excellent arrangement between the measurement and calculated data across all of the field size. And the PDD rate it was a little bit higher and more stable when we use 60-degree wax. One more thing, when we use the gamma index with 1% and 1 millimeter, the rate for PDD is lower for smaller field size, but the rate for the beam profiles is lower for the larger field size. And when we validate Poido, we found that the absolute dose difference is within 1%. It indicates that the model used for the beam deliveries is highly accurate. Finally, for conclusions, we can say that our study confirmed the accuracy of the beam model and dose deliveries from the Electa Scenery Linear Accelerator, whilst highlighting area for improvement such as optimizing the multi-leaf collimator. And continued validation is recommended to maintain accuracy and treatment quality. Thank you for listening.
Hello everyone, my name is Zahra Hassan, and I'm here to present our study with the title of Evaluating the Awareness Levels Among Radiographers Regarding the Proper Handling and Safety Concerns of Radioactive Materials at Salmaniya Medical Complex. As we know, radiographers play a crucial role in medical imaging and therapy, often working with radioactive materials, ensuring their safety and the safety of their patients. This study aimed to assess their awareness regarding relevant protocols and some safety measurements. We conducted a structured survey among radiographers at Salmaniya Medical Complex. The survey included questions about their training, knowledge of safety practices, and handling procedures for radioactive materials. We analyzed the data to evaluate gaps in awareness and understanding. Our findings indicated that while most radiographers were familiar with basic safety protocols, there was a lack of knowledge regarding advanced handling techniques and emergency procedures. Not only that, also a large number of participants reported insufficient training on the latest safety measures and regulations related to the radioactive materials. This highlights the need for ongoing education and training programs. We also observed that many radiographers did not consistently follow safety protocols during their daily operation, which could pose risks not only to themselves but also to their patients and their colleagues. In summary, our results underline the critical need for enhanced training and awareness initiatives. We highly recommend implementing mandatory training workshops focusing on the latest safety guidelines and best practices for handling radioactive materials. We also recommend developing educational resources to continuously inform radiographers about safety protocols and the importance of compliance. Also, establishing systems for radiographers to report safety concerns and suggestions, fostering a culture of safety within the workplace. In conclusion, our study highlights the importance of improving awareness and knowledge among radiographers regarding the radioactive material safety. So by addressing these gaps, we can enhance safety standards in medical imaging and protect both healthcare professionals and patients. Thank you for listening.
Hello. Everyone, today I would like to present my research topic titled dosimetric impact on radiation beam number. Hello everyone. Today, I would like to present my research topic titled Dosimetric Impact on Radiation. Hello everyone. Today, I would like to present my research topic titled Dosimetric Impact on Radiation Beam Number in Intensity Modulated Radiotherapy IMIT Planning for Head and Neck, Breast, and Pelvic Cancer using Hasio-on Linear Accelerator.
Well-respected organizing committee and colleagues, I'm Jiachen Zhou from the Department of Engineering Physics at Tsinghua University. I'm very pleased to have the opportunity to share my recent research findings. This beam diagnostic technology is not intended for patients but is aimed at engineering researchers working on medical accelerators. Well, the part 1 mentioned about for deep and diffuse tumors, higher beam energy requires larger and more complex electron beam accelerators. Tsinghua University has been finished the VEGAS, very impacted gamma ray source. Well, it is the first compact MeV level gamma ray source. Offers high intensity, quasi-monoenergetic, short pulse gamma rays with adjustable energy for medical applications, particularly in tumor treatment. Real-time beam position monitoring is essential due to the need for enhanced interaction between the beam bunch and laser. Well, let's look at part 2. Well, conventional medical accelerators lack effective tools for monitoring and controlling beam parameters. This research introduces the method to monitor beam charge and position before reaching the target. By using a band magnet, horizontal beam position can be conveniently acquired. And 2 detectors were developed, a cavity detector with nanometer level resolution and a strip-line detector with micrometer level resolution. The part 3 is mainly concerned about, well, in ICS light source, cavity and strip-line detectors also called beam position monitors, consisting of detectors, processing electronics, and control systems with non-invasive measurement technology. Tested at TTX and XGLS, the cavity detector achieved position resolution of 713 nanometers in X and 913 nanometers in Y, while the stripline detector achieved 10 micrometers in X and 5 micrometers in Y. The cavity detector offers high precision but limited range, while the stripline detector supports a wide dynamic range with lower accuracy. Well, finally, we think that both of them have promising applications in future high-energy medical accelerators for precise radiotherapy. Well, thanks for watching and listening. Well, respect.
Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. My name is Muhammad Hafiz bin Hanafi, and today I would like to present my research about the quantitative assessment of the 3D printed vial as cost-effective alternative to standardized ACR vial for PET-CT quality assurance. First of all, this study aimed to evaluate the viability of 3D printed vials as a cost-effective and accessible alternative to the standardized American College of Radiology ACR vial that used widely in PET-CT imaging quality assurance. With the rising need for affordable and customized QA tools in resource-limited setting, our research explored whether 3D printed vials can deliver comparable quantitative performance. For the methodology, we analyzed 4 pairs of original ACR and 3D printed vials with equivalent volume and same size. Each vial we activated using the FDG at 370 megabecquerels per mil, and we scanned using the Siemens Biograph PET-CT scanner with identical acquisitions parameter and the clinical setting. SUV max, SUV min, and contrast to noise ratio and the coefficients of variation COV were calculated for each vial, and we do the comparison using statistics with the pair t-test and perform to assess differences in quantitative metrics. For the result, we find that SUV max comparison, there is no statistic significant difference between SUV max of the ACR and also 3D printed vial. The percentage difference between 0.84% to 38.28% with the higher deviations for the smaller size of the vial. For the image quality CNR, we compare across a vials pair with the minimal variations attributed to the background noise. For the SUV heterogeneity, COV, 3D printed vial, exhibit higher COV values, reflecting greater SUV heterogeneity, particularly in the smaller size of the vial. This due to the limitations in the 3D printing, maybe in resolutions and also material uniformity. As a conclusions, we find the demonstrate of the 3D printing vial show the potential as a cost-effective to substitute ACR vials in PET-CT quality assurance. However, the performance was generally comparable And also we suggest the needs for the further refinements, materials, property, and also the printing techniques. This approach could be significant, reduce quality assurance costs, and also especially in resource limited facility like Malaysia. So that's all. Thank you for attention. I'm happy to discuss more further in this research, and please feel free to explore our poster for more details. Thank you.
Hi, my name is Wan Nurain, and I will be presenting this poster with title Skin Dose Assessment using direct. Hi, my name is Wan Nurain, and I will be presenting this poster with title Skin Dose Assessment using direct and indirect measurement for pregnant patients undergoing abdominal fluoroscopy procedure. This study is about the comparison between direct and indirect method for measuring pit skin dose. Two types of direct measuring tools, which are TLD100 and EBT gaphchromic films, are used in this study, while using GE dose wash as indirect PST measurement method. This study was conducted as a preliminary study on the setup of comparing between both direct and indirect method, and also purposely to identify the gap of using TLD100 and EBT3 with dose wash software. 80 chips of TLD were prepared for 3 different regions. EBT films were being cut into 21 × 30 cm and wrapped with transparent plastic. These 2 direct measurement tools were placed at patient abdomen in supine position. Procedure was conducted using abdominal protocol using angiography system. The patient is in her 3rd trimester pregnancy, making the procedure complicated and required longer exposure time. Thus, the need of measuring PST is crucial. After the procedure complete, both TLD100 and EBT3 film were retrieved to be analyzed. TLD100 chips were analyzed using TLD reader Harshaw 3000 in unit nanocoulomb. The calibration curve was obtained and used to convert the value into milligram. Meanwhile, the EBT3 film was analyzed using Epson 10000 expression SL scanner. Then, the film was analyzed using image J with 180 regions of 1 cm × 1 cm ROI. EBT3 film proved to be the gold standard for PST measuring tools due to its most consistent value. The dose wash was giving highest value because the value used in the simulation software was obtained from cumulative IRRMA value at IRP, which is 15 cm from detector towards the tube. This value is proven to be overestimated due to the positioning of patient that usually exceed the IRP. The TLD100 value are giving the lowest value due to its low spatial resolution. The deviation between dose wash and the TLD100 and EBT3 film are 25.16% and 3.66% respectively. As conclusion, the deviation between 2 direct method and indirect method are in a reasonable range. EBT3 film results closer to dose wash compared to TLD100. The variance of TLD100 can be improved by ensuring the whole beam are covered during irradiation. However, both indirect method result in lower PST value compared to direct method. The use of dose wash results in overestimating the PST value in an acceptable percentage between 3 to 25%. The variance is tolerable since it is not significant and the tissue reaction effects are expected. Thank you.
Assalamu alaikum. My name is Riwan Osman Loko from a Department of Physics, Faculty of Natural and Applied Sciences, Nigerian Army University Bio, Borno State, Nigeria. I am going to talk about microstructural, thermal analysis, and gamma ray properties of bricks made of various local natural materials, an approach to repurpose Nigerian and African local materials for application in technology. If you or someone you know is exploring sustainable construction materials and is concerned about radiation shielding and environmental impact, this study will be of interest to you. It focuses on using bricks made from local materials as an effective alternative to lead-based shielding materials. This presentation will cover introduction, aim and objectives of the study, methodology, results and discussion and conclusion. First, let me explain why this study matters. Ionizing radiation poses risks to health by damaging cells and tissues. Traditionally, lead has been used for shielding, but its toxicity and high cost have led researchers to explore safer, more sustainable alternatives. Local materials like clay, granite, basalt, and laterite could provide effective shielding without the downsides of lead. The problem addressed by this research is the need for lead-free, cost-effective shielding materials that can also support environmental sustainability. Natural materials like clay, granite, basalt, and laterite, combined into bricks, could meet these needs while offering structural and thermal stability. The objectives of our study are to characterize the elemental and morphological properties of the bricks, to analyze the crystal structure and thermal stability of the materials, to evaluate the radiation shielding performance of the fabricated bricks. Our method involved collecting materials from Nasarawa State, Nigeria, grinding them into fine powders, and mixing them with water. The mixtures were molded into cylindrical bricks, dried, and then fired in an electric furnace at 1000 degrees Celsius. The fabricated bricks underwent XRD, SEM, and thermal analysis to evaluate their microstructural, thermal, and shielding properties. Our report also showed that the bricks have distinct structural properties. For example, while quartz and feldspar show the effect of granite and basalt bricks, the presence of kaolinite and elite in the XRD pattern emphasizes the contribution of clay and laterite bricks. Serpentine or chlorite indicate a possible metamorphic effect, most likely from basalt. The fabricated bricks in our study have shown different thermal properties based on DTA analysis. For example, clay bricks demonstrated weight changes after 303 degrees Celsius due to dehydroxylation, while laterite exhibited the most noticeable thermal changes at 401.76 degrees Celsius. Our findings also revealed distinct thermal based on TGA analysis of the produced bricks. For example, the study found that granite and mixed bricks start losing weight at lower temperatures, indicating lower thermal stability. Laterite showed the most significant weight loss at 401.76 degrees Celsius, while granite and mixed bricks deteriorated up to 680 degrees Celsius, suggesting diverse thermal behavior. The results revealed that the bricks have good shielding properties. For example, the radiation shielding test showed that thicker bricks, 30 centimeters, could block over 95% of high-energy photons, 1.332 MeV, with granite and basalt having the best shielding ability compared to clay and laterite. In conclusion, bricks made from clay, granite, basalt, and laterite exhibit excellent thermal stability and effective radiation shielding. These materials provide a sustainable, non-toxic, and cost-effective alternative to lead in shielding applications, supporting both technological and environmental advancements. I hope this overview clarifies the potential of local materials in creating safer and more sustainable shielding solutions. Assalamu alaikum.
Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Oluwatobi Adewale Adeba from the King Fahad University of Petroleum and Minerals, Saudi Arabia, and I'm the corresponding author of this research paper, the evaluation of radiation shielding and mechanical properties of palm nut shell ash modelized concrete. And this is a comparative analysis. First of all, I would like to introduce the topic to the listeners. Number one is what is radiation shielding? We know that nowadays, even before now, radiation is one of the most researching area whereby people try to look for a way, maybe modification in order to prevent or shield people, shield human beings from radiation so that they will not be affected by the ionizing radiation. For example, in terms of maybe getting affected by the radiation, or they even use the radiation in order to cure cancers and some other diseases. And you know, this radiation, the radiation absorbed dose strictly rely on the 4 parameters. The number one is the rate of the radiation source. The number 2 is the exposure period, and number 3 is the released photon energy. And another one is the distance between the source to the exposed body and the existence of the what? Shielding material. The last one, which is the existence of the shielding material, that is where we are strictly focusing on. And we all know that based on some researches that have been done or conducted in this area, we know some liver cancers and some other cancers have been treated by this radiation. And we can also minimize this radiation because it is very dangerous and very hazardous to our health. So we need to look for materials in order to shield this radiation, because there are a lot of people working under the radiation. They are being exposed into the radiation. So we need to look for a way to, to shield people, to protect people from this radiation. And that is why we looked, and one of the ways they have been using from the past researches is the cement. They use cement. Cement is a very good shielding material for radiation. But cement only, we discovered that cement only cannot be, we will not do this. Now, that is why we augmented cement with what is called the palm nut shell ash, so that it will increase the properties of the radiation. And at the end of the day, when we split the samples into four samples, the materials into 4 samples by filling the concentration of, the masses of the palm nut shells, and we discovered that there are changes in the properties of the material. For example, when the results revealed that when the content of palm nut shells is increased from 0 to 0.15 kg, now the concrete density decreased from 2.40 to 2.25 gram per centimeter cube. Even the porosity as well, there will be decrease in density, and there will be decrease in porosity as well, so that the material will have enough space or pores in order to absorb a lot of water in terms of maybe doing curing, so that the material will have a very strong, it will be very strong, and it will be very durable. And another thing is that when it's like this, and palm nut shell also have some other elements which are very beneficial into this, so like magnesium, potassium, and some other like that. So they are very strong material. So, and with this result that we have already captured here in the poster, then we discovered that the study presented a detailed insight for the optimized performance of the concrete, displaying its prospects for the purpose of shielding of gamma radiation. Thank you.
Study of the influence of micro and nanoscale zinc oxide particles on the radiation shielding capability of diboron trioxide, lead oxide, barium oxide, zinc oxide glass system. Abstract. In the present work, a new glass series consisting of 45 mol% diboron trioxide, 20 mol% lead oxide, 15 mol% barium oxide, and 20 mol% zinc oxide was fabricated using zinc oxide particles of varying sizes, 20 micrometer micro zinc oxide, 20 nanometer nano zinc oxide, and a combination of 10 micrometer plus 10 nanometer zinc oxide. 3 glass samples were fabricated with different thicknesses. The ionizing photon shielding ability was measured experimentally using various point gamma sources, including americium, cobalt, and cesium, along with high purity germanium detector. The radiation shielding efficiency of all 3 glasses was determined with the sample containing nano zinc oxide exhibiting the highest radiation shielding efficiency. The relative deviation among the nano, micro, and nano micro composite glasses was analyzed with the nano glasses exhibiting higher linear attenuation values across all energies. Study of the influence of micro and nano.
Hi, my name is Mohammed Safi, worked as Faculty of Science, Alexandria University in Egypt. The impact of lead oxide in porate glass system to determine the physical, mechanical, and shielding characterization. In this work, we prepared this glass by melt-quenching rule, as shown in this figure, and determine the shielding properties and calculate the mechanical properties. The mechanical properties were calculated by Mashima McKenzie, and the attenuation properties was measured by narrow beam technique. The results of this work of mechanical was enhanced, as well as the attenuation parameters was enhanced by heating or increase the lead oxide percentage. In this work, we can conclude the increasing of lead oxide content in this glass system significantly enhances their density, elastic properties, and gamma radiation shielding performance. Higher lead oxide concentrations improve attenuation at lower gamma energies, with complete shielding achieved at 0.059 million electron volt. However, attenuation decreases at high energy, with maximum transmission observed at 1.33 million electron volt. These findings demonstrate the potential of lead oxide enriched glasses for effective radiation shielding, especially at low gamma energy levels. Thank you for your listening, and any questions, you are welcome. Thank you.
Greetings, I'm Mohammed Ibrahim, a bachelor student at the Faculty of Science, Alexandria University in Egypt. Optimizing radiation shielding, superior performance of nanoscale lead oxide, bismuth trioxide, and tungsten oxide composites. In this study, we have investigated the radiation attenuation capability of composite materials containing the lead oxide, bismuth trioxide, and tungsten oxide, formulated as solid-shaped pellets composed of micro and nano-sized powders. All the samples we have used had the same mass and radius, but varied in thickness. A hyperpure germanium detector was used to measure the number of photons penetrating the samples, with photon energies selected in the range of 60 to about 1300 keV from americium, cobalt, and cesium gamma ray sources. Our evaluation focused on empirically comparing the radiation shielding properties of micro and nanosite samples using 6 parameters: linear attenuation coefficient, the mean free path, half-value layer, 10th value layer, transmission factor, and the radiation shielding efficiency. The samples used were solid pellets from metal oxide, nano and micro powders, and they were crafted via powder compression using a hydraulic press machine. Data obtained from the detector was used to calculate the following radiation shielding parameters, which is shown in these tables for each of the compound we used. And we have plotted some of our results to better show the trend that the radiation shielding parameters take across different energies we used. Results obtained demonstrates the superiority of using nanoscale particles over microscale particles for the same compound, which is more noticeable at higher energies relative to microscale properties, as shown in the figures before. While across all compounds we used, we found that lead oxide is best used at low energies, while at higher energies, tungsten oxide had the better attenuation properties. In conclusion, the analysis we have done on the data showed an obvious superiority of nanocomposites, which means that we can make lighter and more efficient shields using the nano-sized composites. Finally, for any questions, please feel free to email me, and thank you.
Assessing the radiation shielding potential of porate glasses enhanced with lead dioxide, barium oxide. Assessing the radiation shielding potential of porate glasses enhanced with lead dioxide, barium oxide, and yttrium-3 oxide additives. As radiation is increasingly used across various professions, it is essential to develop effective radiation shields that protect patients and employees from high-energy photon exposure. Glass is one of the most common materials used for radiation shielding, especially those containing heavy metal oxides. In this work, we developed new porate glasses for radiation shielding, doped with heavy metal oxides, lead dioxide and barium oxide, and a rare earth oxide, yttrium-3 oxide. The radiation shielding properties of the prepared glasses were experimentally measured using an HPG detector and various radioactive sources. The results showed that the linear attenuation coefficient is high at 0.059 mega-electron-volt, ranging from 13.662 to 17.979 centimeters to the power -1, and decreases with increasing energy, reaching minimum values between 0.204 and 0.235 centimeters to the power -1 at 1.333 mega-electron-volt. The chemical composition is a major factor affecting the linear attenuation coefficient, with results showing that the linear attenuation coefficient increases as more lead dioxide, barium oxide, and yttrium-3 oxide are added to the glasses. This suggests that increasing the amounts of these three components enhances the glass's radiation shielding performance. The half-value layer of the prepared glasses is very small at 0.059 megaelectron-volt, ranging between 0.039 and 0.051 centimeters.
Today I'll be presenting our study titled Application of Volumetric Modulated Arc Therapy, VMAT, for Craniospinal Irradiation, CSI, using Elekta Synergy at Hughes Central Hospital. Craniospinal irradiation, CSI, is a cornerstone technique in radiotherapy for treating central nervous system malignancies, such as medulloblastoma and brain tumors with meningeal spread potential. Traditional 3D conformal radiotherapy, 3D CRT, while effective, often involves multiple field junctions, leading to challenges like dose inhomogeneity and increased radiation exposure to healthy tissues. To address these limitations, we investigated the use of VMAT on the Elekta Synergy 160 leaf agility MLC at Hughes Central Hospital, aiming to improve treatment quality, safety, and efficiency. Methods. In our study, we treated 5 pediatric patients with a prescribed dose of 23.4 GY in 13 fractions. Immobilization, achieved using vacuum bags and thermoplastic masks, ensuring precise positioning in the supine position. Treatment planning, performed using CT scans with 3 mm slice thickness and planned using Monaco V6, 1, 4.0. VMAT plans utilized 2 isocenters with overlapping arcs to achieve comprehensive craniospinal coverage. Key parameters. We analyzed conformity index, CI, homogeneity index, HI, monitor units, MU, and doses to organs at risk, ORs. We also evaluated uncertainties, such as simulated +3 mm patient shifts. Results. The results demonstrated excellent treatment outcomes. Target volume coverage. PTV coverage was outstanding, with V95% averaging 99.27%. Hotspot volumes were minimized, with V107% at 1.96% and V110% at just 0.05%. Plan quality, CI averaged 0.93, and HSA averaged 1.06, reflecting exceptional conformity and dose uniformity. OR sparing, critical structures including the lenses, lungs, heart, and kidneys, received doses within safe limits, reducing potential long-term side effects. Treatment efficiency, an average of 1,197.56 monitor units, demonstrated the practicality and efficiency of VMAT for CSI. Conclusion. This study highlights the successful implementation of VMAT for CSI using the Elekta Synergy system at Hughes Central Hospital. Our findings show excellent PTV coverage, minimal hotspots, and high-quality treatment plans, effective sparing of ORs, ensuring safety and reduced risk of complications, practical and efficient treatment delivery with VMAT. In summary, this approach offers a promising solution for improving the outcomes of craniospinal irradiation in pediatric patients, addressing challenges posed by traditional techniques. Thank you for your attention, and I'm happy to answer any questions. Hello, everyone.
Hello everyone. The title of this poster paper is Dose Assessment of the Helper in Veterinary X-ray Room during the X-ray examination.
Hi everyone, my name is Turki Al-Matani. I am going to present our study on the Monte Carlo simulation of head scatter and radiation leakage of a 6 MV photon beam from an agility head using a Fluka Monte Carlo code. It's known that radiotherapy using LINAC is highly effective for cancer treatment. However, unintended radiation exposure outside the treatment field can pose risks such as secondary cancers. While most studies focus on in-field dosimetry, there is a gap in understanding LINAC leakage and out-of-field radiation modeling. Regularity guidelines state that LINAC leakage should not exceed 0.1% of the useful beam. Our study aims to analyze LINAC leakage radiation using Monte Carlo and determine the required lead shielding thickness to meet these limits. For the methodology, we used Elekta Synergy LINAC at Singleton Hospital, Swansea, UK. The LINAC is equipped with an agility head. Leakage radiation was measured using spherical ion chamber, TK30, and the measurements were taken at different angles as shown in figure 1A. And the results were compared to the reference dose at the isocenter under standard conditions. For the Monte Carlo simulation, we modeled the LINAC head, including most of its component using Fluka, as shown in figure 1B. And the required lid thickness was determined by considering the linear attenuation coefficients and build-up factors to account for the broad beam conditions. The results showed that the required lid thickness to reduce leakage varied with the angle. For example, for 90 degrees, it requires 13 centimeters, while for 45 degrees, it requires 7.7 centimeters. Table 1 shows the leakage comparison between the measurement and Monte Carlo at these positions, at these different angles. And the largest differences between the measurement and Monte Carlo was found at the isocenter, where the uncertainty, statistical uncertainty was approximately 70%. The differences could be due to the limitation of the Monte Carlo model of the MLC, which it does not take into account the leakage between the leaves. Also, it could be due to the fact that the ion chamber does not have a uniform response outside the 48 kiloelectron volt to cobalt 60 energy range. In addition, the simulation efficiency can be improved by reducing dependency on photon track length and instead using energy fluence and mass energy absorption coefficient at each position, at each angle. In conclusion, this study successfully modeled and measured LINAC leakage radiation using experimental and Monte Carlo simulation approaches. The result emphasized the need for varying lead shielding thickness to comply with the regularity limits. Further improvement in MLC modeling and simulation efficiency would enhance the accuracy and reliability of these simulations. Thank you for your time.
Good afternoon, everyone. My name is Shahad Al-Rashid. Today I'm gonna present our poster with my colleague Amjad Al-Mutairi and Mudawi Al-Qahtani. Our poster is about volumetric modality arc therapy for total body irradiation versus conventional TBI. I'll start with some introduction. Total body irradiation is an integral part of conditioning regimen for hematopoietic stem cell transplant. Volumetric modality arc therapy is a modern technique used to deliver TBI, promising improved dose distribution compared to the conventional method. Our research question is to compare the effectiveness and the challenges of the VMAT versus conventional TBI in the treating a 3-year-old pediatric patient diagnosed with acute lymphoid leukemia. I'll go through our methodology. The patient is a 3-year-old female with acute lymphoid leukemia undergoing HSCT. Treatment plan, we used VMAT using 5-6 MV photon dynamic arc. Total dose 12 gray delivered in fractions over 3 days. Treatment volume, head, chest, abdomen, pelvis, and lower extremities. Procedure, treatment performed under the general anesthesia with the patient positioned accurately for each session. Treatment took approximately 2 to 3 hours per fraction compared to the conventional TBI of 40 minutes. Our finding is VMAT provided a superior dose distribution compared to the conventional TBI, ensuring better coverage for the target volume. However, the prolonged treatment time of 2 to 3 hours per fraction compared to the 40 minutes of conventional TBI led to increase the risk of setup and random errors. Challenges including maintaining patient positioning due to the movement anesthesia adjustment and the need for the constant monitoring. These difficulties highlighted the importance of coordinations with the radiation therapy team to ensure the accurate treatment delivery. To conclude, VMAT for pediatric TBI offer a superior dose distribution compared to the conventional method, but its increased complexity and longer treatment time pose challenges. Maintaining precise patient positioning and managing risk like setup error require a skilled radiation therapy team and carefully monitoring, while promoting the VMAT use in pediatric patients should be carefully considered due to these challenges. Good afternoon, everyone.
Hello everyone, my name is Mehdi Hassanpour, PhD student at UCAM University in Malaysia. I would like to present my research entitled Advanced Nuclear Beam Analysis for Radon Detection. Radon is a radioactive gas naturally found in environment like air, water, ice, and even vacuum. Its ability to accumulate in enclosed space poses serious health risk, particularly lung cancer. Conventional methods for detecting radon face technical challenges, including high cost and limited applicability to real-world conditions. This study aimed to address these challenges. In this study, we employed two techniques: STIM, where protons lose energy at the pass through the target, and RBS, where protons scattered back with a change in energy. To reduce experimental cost and control parameter, Monte Carlo simulation MCMPX were applied to study radon detection in water, air, ice, and vacuum. The result identified characteristic energy for detecting radon such as 16.21 MeV in water and 9.49 MeV in air. In most cases, proton transmission probability decreases as radon concentration increases. However, an exception was observed and at 15.69 MeV in water, where the transmission probability showed an increasing trend due to reduced proton absorption cross-section. This research highlights the potential of advanced nuclear technique for radon detection, identifying characteristic energy that enhance precision while reducing cost. This method can be valuable for environment.
Thank you all for listening.
Thank you, Iman.